Hello everyone, welcome back to the second session on free space optical communication. Today we will understand how an FSO system operates, what major components are involved at the transmitter and receiver, and how the overall system performance is evaluated using power budget analysis. Free space optics is an advanced wireless communication technology that transmits data in the form of light through free space such as air or vacuum instead of using optical fiber cables. It combines the high bandwidth capability of optical fiber communication with the flexibility of wireless transmission, making it highly useful for modern high-speed communication needs. Let us briefly look at the outline of today's presentation. Block diagram of FSO system, transmitter components, laser diodes, LEDs, optical modulators, receiver components, photodiodes, PIN and APD, optical filters, optical sources and detectors, optical beam formation and alignment, power budget analysis. We will proceed step by step to understand how each component contributes to the overall functioning of the FSO system. Let us begin by understanding the overall structure of an FSO system. The complete system consists of a transmitter section, an atmospheric channel, and a receiver section. The data to be transmitted, whether it is voice, video, or digital information, is first generated by a source. This electrical data signal is then modulated onto an optical carrier generated by either a laser diode or a light-emitting diode (LED). After modulation, the optical signal is transmitted through the atmosphere in the form of a narrow beam optical signal. At the receiving end, the optical signal is collected using receiver optics and focused onto a photodetector. The detector then converts the optical signal back into electrical signal, and finally the original data is recovered. The performance of the transmitter depends on several important parameters such as size, output power, laser intensity, beam quality, and beam divergence. Beam divergence refers to how much the beam spreads as it propagates through space. Lower divergence ensures that more optical power reaches the receiver. On the receiver side, two important factors are the aperture size and the field of view of the detector. The aperture size determines how much light can be collected, while the field of view determines how much background noise may also enter the system. Now, let us understand the optical sources used in FSO systems. One of the simplest sources is light-emitting diode, that is LED. An LED is a semiconductor device that emits light when electric current passes through it. It works on the principle of electroluminescence, where electrical energy is directly converted into light energy. When electrons recombine with holes within the semiconductor material, photons are released, thereby producing light. LEDs are inexpensive, consume less power, and are suitable for short-range communication systems. The color of the emitted light depends on the bandgap energy of the semiconductor material. However, they produce a wider beam and lower optical intensity compared to lasers, which limits their use in long-distance high-speed communication. The other important optical source is the laser, which stands for light amplification by stimulated emission of radiation. A laser produces an intense, coherent, monochromatic, and highly directional beam of light. It operates on the principle of stimulated emission. In this process, excited electrons release photons and these photons stimulate other excited electrons to emit identical photons, leading to amplification. Lasers use an optical cavity with mirrors to provide feedback and sustain the emission process. Lasers have a wide range of applications in modern technology. They are used in laser printing, barcode scanning, optical storage, CDs and DVDs, fiber optic communication, and medical procedures like laser eye surgery. They are also used in measurement systems, scientific research, military targeting, and industrial cutting and welding. Compared to LEDs, lasers require more power and a controlled feedback mechanism, but they provide superior beam quality and narrow divergence. This makes lasers ideal for long-range, high-speed FSO links. When choosing between LED and laser diodes as a light source, the selection depends on the targeted application, performance requirement, cost, and reliability considerations. For long-range gigabit speed point-to-point FSO systems, laser diodes are essential due to their high intensity and narrow beam divergence. For short-range systems where cost and simplicity are more important, LED-based systems can provide satisfactory performance while reducing system size and overall cost. Thus, the choice of optical source must align with the communication requirements. Next, we move to optical modulators, which are critical components in the transmitter section. The main function of an optical modulator is to map digital data onto the laser beam. Instead of simply turning the laser on and off directly, external modulation techniques can be used to improve performance. Optical modulators enhance signal quality by reducing chirping effects and improving extinction ratios. As data rates increase, the limitations of optoelectronic components become significant. Therefore, selecting appropriate modulation and detection hardware becomes essential in high-speed optical communication systems. There are two main types of modulation techniques: direct modulation and external modulation. In direct modulation, the drive current of the laser diode is varied accordingly to the input's data signal. This method is relatively simple and cost-effective, but may introduce frequency chirping and limit the performance at high data rates. In external modulation, the laser produces a continuous optical signal and an external device modulates the light. External modulation offers higher performance, reduced distortion, and better signal integrity, making it suitable for high-speed FSO systems. Some of the key modulators used in FSO systems include the Mach-Zehnder modulator (MZM), electro-absorption modulator (EAM), and acousto-optic modulator (AOM). The Mach-Zehnder modulator operates on the principle of optical interference and provides high bandwidth, making it widely used in high-speed systems. MZM is often used in conjunction with advanced modulation schemes for generating duo-binary signals. The electro-absorption modulator is compact and efficient and can often be integrated with laser sources. The acousto-optic modulator modulates the intensity, frequency, and direction of a laser beam by creating a diffraction grating, often applied to enhance system security and performance through beam steering. Now, let us discuss the receiver side of the FSO system. The choices for detector materials are more limited compared to transmitter sources. The most commonly used materials in the near-infrared spectral range are silicon and indium gallium arsenide. Germanium is another material that has been used in some systems, but it is less preferred due to high dark current values. Unlike lasers, detectors have a broad spectral response and are not tuned to a specific wavelength. The two most common photodetectors used in FSO systems are pin photodiodes and avalanche photodiodes (APDs). Pin photodiodes provide fast response time with moderate sensitivity and are widely used due to their excellent balance between performance and cost. Avalanche photodiodes, on the other hand, have an internal gain mechanism that provides much higher sensitivity. This makes APDs ideal for detecting weak signals over long distances or under challenging atmospheric conditions. However, APDs require higher bias voltage and are more expensive. Optical filters are also used in the receiver to reduce background noise from sunlight and other interference sources. By allowing only the desired wavelength to pass through, optical filters significantly improve the signal-to-noise ratio, leading to cleaner data recovery. FSO systems largely utilize components adapted from fiber optic communication technology. Semiconductor laser diodes are used for emission, while PIN or APD photodiodes are used for detection. These components ensure high modulation bandwidth, narrow beam divergence, and efficient atmospheric transmission. Most FSO systems operate in the near-infrared wavelengths such as 850 nanometer, 1310 nanometer, and 1550 nanometer. These wavelengths minimize atmospheric scattering and take advantage of the mature fiber optic technology. The 1550 nanometer wavelength is particularly preferred due to its lower atmospheric attenuation and better eye safety characteristics. Optical sources include laser diodes, vertical cavity surface emitting lasers, distributed feedback lasers. Laser diode is the primary source for FSO, offering higher power, narrow spectral width, and high speed modulation capabilities. Vertical cavity surface emitting lasers are used for shorter range, lower power applications due to their low cost and low power consumption. Distributed feedback lasers are used for long range, high bandwidth FSO, providing very narrow spectral lines and high stability. Detectors include positive, intrinsic, negative pin photodiodes, which are used for shorter range FSO, offering good linearity, lower cost, and simple design. Avalanche photodiodes are preferred for long range FSO due to their internal gain mechanism, which significantly improves sensitivity and signal to noise ratio. Photomultiplier tubes (PMTs), which are used for very long range, high sensitivity applications, for example, deep space communication. Optical beam formation and alignment are crucial aspects of FSO systems. Beam divergence must be carefully controlled to prevent excessive spreading of the optical signal. Collimating optics are used to convert diverging beams into parallel beams for long-distance transmission. Fine alignment mechanisms and precision pointing systems are necessary to ensure accurate alignment between transmitter and receiver. Even small misalignments due to building sway or external environmental factors can cause significant signal loss. Finally, we come to power budget analysis, which determines whether an FSO link will function reliably. The power budget is calculated by subtracting total losses from the transmit power and comparing the result with receiver sensitivity. Losses include beam divergence loss, atmospheric attenuation due to fog, rain, dust, and pointing errors. For example, if a transmit power is 10 dBm, the path loss is 20 dB, and the receiver sensitivity is minus 30 dBm. The system achieves a 0 dB margin. A zero margin indicates that the system is barely operational and requires optimization. To improve link reliability, one can increase transmit power, use better optics, improve alignment, or select more sensitive detectors. Maintaining a sufficient link margin ensures stable communication even under adverse weather conditions. In conclusion, free space optics is a powerful, high-speed wireless communication technology that bridges the gap between fiber optics and radio frequency systems. The performance of an FSO system depends on careful selection of optical sources, detector sensitivity, precise alignment, and accurate link design. As future engineers, understanding FSO system equips you with the knowledge of next generation optical wireless communication technologies that will play a significant role in 5G, 6G and beyond. Thank you and have a wonderful day.